Okay, so today is talking about interpreting graphs. So this is all just like reading graphs and different things like that. So we'll just go through some of these examples and do them. There's only like 12 topics. I believe the next one is about constructing them. So you actually go make them, which Alex has tools, which are really cool and work very easy for us to do. Okay. Biggest thing here is just being careful of the different words. So we'll just go through, like I said, a bunch of the examples here and go from there. So this graph shows the number of orders received by a company for the last 5 months. What was the greatest number of orders in a month? I think we'll go into this later, but this is your x-axis. The x-axis is the horizontal one. And I say this because I think the last topic of this is kind of hard. Your vertical axis. Your vertical axis is your y1. Okay, so there is some talk about the y1. So usually you put the label on the x-axis and the number, how much it's going up or down on the y-axis. So this right here would be the highest one, and it looks like it's about in between 1900 and 2000. So what, like 1950? Okay, so you have to read the graph, and just a lot of this is just starting to read the graph. When did the greatest increase in orders occur? So this is when did the line go the biggest between 1 month to the next month. I would say it's this one, right? This one looks like it goes up higher than this one. This one kind of looks a little sideways. So I would say it's that one. So it would be August to September. Okay. So most of y'all are doing fine. Most of y'all probably tested out of a lot of these topics. These are ones that you usually test out of. Like this next one. I shouldn't even work this next one. But since I'm recording and doing notes, I will go ahead and work all of these real quick. Oh, no, I just closed out of Alex. I was closing out of some tabs, and I closed out of Alex. Man. Okay, so the next one is interpreting a tally table. Again, super easy. I'm sure you tested out of this one. If you didn't, that's fine. Not a big deal. Tammy asked her classmates to choose their favorite flavor. So this is just different ways to do graph. I guess I should have said this too. Like on last week, we talked about collecting data. So this week's all about organizing the data. So the first way we do that is with graphs. So how many students chose grape? So how many students chose grape? So you just go to grape here. Obviously, you count, 5, and 1. So 5 plus 5 plus 1 equals 11. Again, y'all get the luxury of me recording, so I am probably going to do all these problems, but I'm only going to do those once if they're super easy. Sorry. 1 second to get back to my screen I exit out of. Oh, wait, that's not the next one. The next one is this one. Okay, next one is interpreting a bar graph. So this is reading a bar graph. So what we'll get to towards the end of this is like how people kind of trick you with different graphs and different things like this. We live in a very fast society of, we scroll fast, we get reels, we get things like this. Nothing lasts over more than 10 or 15 seconds. So you can kind of trick people by just looking at a graph real quick. And we'll talk about that either today or the next time. So a bar graph, same idea here. You just make bars, same idea as a line graph. Which state has the most sales? So this would be Colorado. How many does it have? So you go over here and it would be 12. How many more sales agents are in Indiana than in Maryland? So Indiana has 6 and Maryland has right here at 5. So it looks like 1, right? 6 minus 5. How many states have more than 6? So 6 is...
Professor, wouldn't it be 3 for Maryland?
Oh, it is 3. Thank you. Stop me. See, I say they're easy and then I mess stuff up. 2 between 4 and 2 is 3, not 4 and not 5, right? So 6 minus 3 would be 3. Thank you. Just going fast there on these easy ones and messed up. Okay. How many more states have more than 6? So Indiana and Arizona have 6, But since it says more than 6, the only one would be Colorado. Okay, so you would not include 6 because it says more than 6. Interpreting a double bar graph. All right, a double bar graph is very similar. This is one that a lot of people like to use because you can put a lot of information on it. In one spot. So this one comparing like males and females employees. Trying to make it bigger here for you. All right. Which departments have more females than males? Check all that apply. So one thing that you always check if a graph is good, it should have like a key somewhere. So like the purple is the males and the red / the candy cane looking ones are females. So they should have some kind of key to tell you stuff on there. Which department have more females than males? So this is where the candy cane one would be bigger than the purple one. So those two, advertising and marketing, the candy cane is higher. I probably shouldn't call it candy cane. That makes me want Christmas to be here, but that's fine. All right. Next one, which departments have more than 200 females? So again, like you got to find your keywords here. More than 200. I guess we need the females here too because that tells us which graph to look at. So 200 is right here. Anything higher than that, or a candy cane one higher than that, it would only be this one right here. It'd be only marketing. And the last one, estimate the total number of employees in accounting. So this is just the total number of employees. So you would do males plus females. I'm down here at the bottom of my screen. It's not letting me write. Males plus females. So in accounting, okay, when it says to estimate, you just want to get as close as you can. They say to estimate because this is kind of hard right here. I'm going to cheat and I can make a straight line. But accounting, I don't know, what did you say? It's a little more than half. So we could say the males is at about 80. And the females are about 50. So if I had to guess, like 130, 135, somewhere in that range, you could probably go a little higher. It will have some leeway. Alex will count a range of values there. So 130 to 140 probably is a good number there. Not so bad so far, right? Finding a percent of a circle graph. Is this the one that's hard? No, I think I deleted the one that's hard. So this one, you do have to be careful in Alex the way they do this, and maybe I'll generate a different one to show you. But what amount is budgeted for clothing? Okay, so it says that the circle graph shows a family budget of its annual income. If the total amount is 150, trying to highlight. Total amount is 150. How much is budgeted for clothing? Okay. So we come over here and we say, okay, clothing is 15%. So what you would do on this one is 150,000 times 15%, and that would tell you how much money is budgeted for clothing. 15000. So that is $22,500. Wouldn't it be nice to spend $22,000 on clothes? That's done. Copy and delete. Hold on, I wanted to generate another one. That's the same thing. Same thing. Same thing. Sorry, I was trying to see if it would give me a different variation. Okay, it's not going to, so looks pretty much the same on there. What's next? Relative frequency histograms. Okay, so a lot of the stuff that we've done so far, I guess I should flash back for a second because not a lot of it. So the first 3 or so that we did, I guess most of the ones we've done so far, are, remember, qualitative or categorical variables where you can put them into categories. You can put the males in this group and count them. You can tell what percentage there are. Even the circle graph, you can put how much you spend on clothing here, how much you spend on housing here, the different flavors of whatever that is, ice cream. They're just their favorite flavor. Doesn't say of ice cream or what. The month. So you can put, those are all categorical because you can put them in their own category. So what happens when you get to a quantitative one, when you have more numbers to deal with? There's a little bit more that you can do. And we've done bar graphs, we did double bar graphs. What they call a quantitative bar graph is called a histogram because we're dealing with numbers here. Okay. So on this one right here, and this one, I know they trick you on the different ways they do this. Can y'all see that okay, or do I need to try to make it bigger? No, you can't see it? Can you see it? Okay-ish? Okay, thank you. All right, so we don't have to read all this problem, but there's 50 total students. Like, I can go ahead and just identify the keywords here. There's 50 sampled students, so there's 50 total. It says, based on the histogram, find the proportion of math test scores in the sample that are less than 650. Okay, so here's where this gets a little tricky on this one. So less than 650, you got to make sure you read these right. A histogram is basically a bar graph that touches. That's because like 649 to 650 is on this one, but then 651 is right on this one. So it goes to the next one, okay? So 650 or less would be anything here to the left. So I'm going to add up those two numbers, 0, 10, and 0. So it's 10% plus 24%. My answer would be 34. The proportion would be 34. All right. So not super difficult, but you're doing this problem. You're going through it. And let me show you what happens. You get to this next problem, and you answer it. And you get it wrong. So on this one, you have a sample of 25 post offices. Find the proportion of waiting times in the sample that are greater than or equal to 12. Greater than or equal to 12. Okay, so greater than or equal to 12, you come over here, 12 greater than, you do what we just did, it's 8 plus 3 plus 3, that's 14, okay? Can anybody tell me when I put in 14 why it's wrong? No, not in the mood today.
Like of 25
This is asking for proportion. So a proportion would mean that I do need to divide it by the total amount. So 14 times 4 is 56. Okay, so this would be, whoops, I guess I need a 0 there. 0.56. Okay, so it'd be 56% or the proportion 0.56. So what this one does is it switches back and forth. So the key word here is this. This says it's a frequency chart. This says it's a frequency chart. If I go back to the other one, if I go back to this one, it says it's a relative frequency, okay? So this is one of the definitions that they use. I did put some definitions at the top of this page, but that's our first one. The frequency counts, and the relative frequency is a stats word for percentage. So if you see the word like relative frequency, it is talking about a percentage, okay? So that is the difference right there. They'll switch those up on you and give you a frequency one, and that's just the number. And then the relative frequency is going to be the percentage or the proportion, so it's like a decimal. So if they give you the decimal, and I'll come back there in just a second, that's fine. If they give you the decimal, like the graph has decimals on this one, then I don't have to divide because it's already in proportions. Whereas this one below here, I don't know why it's not letting me scroll down. Technology does not like me today. This one, the second one, gives you the number, so you actually have to divide it by the total. Okay, so be careful on that topic. That will mess with you. Next topic, shapes of distribution. Let me draw some stuff here. All right, so one of the most common shapes in statistics is called a, there's a bunch of different names for it actually. But you have this shape, and this is like if even a bar graph would look like this, I could kind of draw this shape on it. They call this a bell-shaped distribution. A bell-shaped distribution. This is also, I'm going to put it right here, but we don't talk about this till like chapter 7 or 6, something like that. It's called a normal curve. So what happens here is all the data. So like we said, we only can sample so many people. We can't ask that many people. All data starts to turn into this. Like if you ask enough people, if you collect enough data, it'll always turn into this. And what this is saying is that, okay, the majority of people or data right here is going to fall around the average. You're going to have a few extremes on the high end and a few extremes on the left end. So no matter what data looks like, it always starts to look like this if you ask enough people. You may have to ask 10,000 people, but it will start to look like this. I don't know if I want to say this quite yet, but I'm going to. I'm skipping ahead just a little bit, but y'all know these words. Mean and median, right? Okay, the mean is the average. Y'all know you add them all up and divide by how many there are. Can somebody tell me what the median is? The middle number. You line them up from least to greatest, and it's the middle number. On a perfectly shaped bell graph, we're going to we'll spend next week on talking about mean and median and all that good stuff. But on a perfectly shaped bell graph, the mean is about the same thing as the median. On perfectly shaped, they are equal, okay? And we'll come back probably and hit that again later on. The other big one, this one, they call this a left skewed distribution, or skewed left. Probably would make more sense. Skewed left. Skewed left. Okay, so you say, well, did I mix it up because the skewed right? Skewed right looks like this. Okay. And you'd think I mixed it up because when I look at this, all my data is over here on the right, but I wrote skewed left, right? All my data is over here on the left, but I wrote skewed right. So what happens here is to identify these, you find the peak. Okay, you want to find the peak. You find the peak and tail longer on the left, so it's skewed left. Okay. Same thing here. If you find the peak, tail longer on the right, so it's skewed right. That's the easiest way to identify them when you're looking at them. But what happens, or the reason they really call that is, let's say y'all take a test and it's really, really easy and everybody scores super high, right? The mean would be about right here in the middle. I'm sorry, it'd be about right there where the peak is. But somebody scored really bad on it, which is going to drop my average down. Okay? I'm sorry, the median would be in the middle, and the mean would get pulled to the left. So what happens on skewed left, the mean gets pulled to the left. The mean is less than the median. And again, I know we haven't talked a lot about mean and median yet, but we will next week. I just knew y'all knew those words. So my mean gets pulled to the left, and that is why they call it skewed left. If everybody scores really high, but then a couple people score low on a test, it pulls the average down. Okay, same thing here. My median's around the peak, but my mean, the tail is pulling it right. So maybe this is a really hard test that y'all failed and everybody did bad, but a couple people did good, and that's going to pull the average up. Okay, and we'll go into a lot more detail on that. So my average is actually higher than the median. The mean's higher than the median on this one. That is why they say skewed left and skewed left, because the tail being longer pulls the mean to the left. This one, the tail's longer on the right, so it pulls the mean to the right. So those are the common ones. A couple more just to write some stuff that I don't think you'll see too much. This one is called a uniform. This is like if I don't know, took a poll and I marked how long everybody's been to class. This is our third class, so everybody'd say 3, right? I get a 3 for everybody across. The example like a book uses is like someone a guy, businessman that gets his hair cut every 2 weeks. Like his hair's not going to change that much. It'd be 18 centimeters, 19, 20. Like it's just going to be about the same. They do use a lot of words like approximately because it's hard in real life data to get exactly right. And then the last one here would be something that looks like this. I think these are all the ones we got to talk about. This is called bimodal. Okay, we said mean median. What's the other word that goes along with that? Mode. So somebody tell me what the mode is? Again, this is all next week stuff, but that's fine. Anybody remember what the mode is? What'd you say? Yeah, the one that occurs the most. The number that you see the most often. Okay. Again, if you don't know that, we're doing that next week, so that's fine. So this one actually creates 2 peaks. Most data only has 1 peak. This one creates 2 peaks. Some real life data that would do this. Average shoe size or average height, right? We'll do height. Average height. There's a peak where the females are and there's a peak where the males are, because generally the average female height is a little bit less than the average male height. I said shoe size because same thing. The males generally have larger feet than females. So like there's a peak where the female averages and there's a peak where the male averages. So that creates a bimodal graph. All right, I think those are the main ones that we'll see on this topic. So let's go do this topic real quick and see. Where's it at? Shapes and distributions. So this one gives us 3 graphs. So this is what you have to do is kind of think about how to draw that shape that I just drew on these graphs. So like if I was going to draw a quick shape of these real quick before we even get started, this one would look like this. This one kind of has that uniform shape to it, right? This one would be like this. So without even like looking at the things right now, I would say this one, the peak is over here and the tail's longer on the right. So I would call this one skewed right. So where the tail's longer is the direction. This one I would say is about uniform. Like it's okay if it's a little bit off. It's approximately uniform. And this one is probably one of those bimodal examples because there are kind of 2 random peaks on it. All right. Which histogram is the closest to being uniform? Okay, well, we answered that already. B. Which histogram is closest to being symmetric? Symmetric, we did not talk about. That's the other word I need to write under bell shape. But symmetric means you can fold it in half, right? It's symmetric, you fold it in half and it matches up. So the closest one probably is going to be B. Which histogram is described as unimodal? So that means like a unimodal. Unimodal is like a unicycle, 1 wheel, right? So 1 peak. Okay, so that means 1 peak. And that would be A, right? A only has 1 peak. Which histogram is skewed to the right the most? And that would also be A. Okay, so I never answered C on this. That will happen on some of these. So just be careful with your answers there. I am going to go back and write the word symmetric right here, because this bell shape is symmetric. We'll spend chapter 7, 8, 9 is all about the normal curve, so we'll spend a lot of time with that. So far, they're pretty similar to what we just saw. Let's do this one. All right, so like if you want to go through them real quick, I would say this one is a bimodal. This one, any guesses? I would say that one is bell-shaped. That one's pretty symmetric. It's not going to be perfect. And then this one would skewed which way? Right. Find the peak. Okay, find the peak, and the tail's longer on the right, so it's skewed right. All right. Which histogram is skewed to the right the most? That would be C. Which one's closest to being symmetric? That's usually the bell-shaped one. Which one is bell-shaped? That's B. And which one is bimodal? So that is A. Okay. So you just got to look at those and get the general shape of those. And those, what the point of these graphs and different things is to show you that you can start to determine something about the data by just looking at this. And again, this is kind of jumping into next week, but it kind of just all blends together. On the bell-shaped one, I know my mean and median are about the same. So like I know that by just looking at the graph. On the skewed right one, it's right, so my mean is going to get pulled to the right. My mean is going to be bigger than the median. I can start to tell all that by just looking at the graph. Okay. All right. I think there's a super easy one before the hard one. We've done, why is that one in there? Okay, that's fine. There is one constructing one in here. Must just got slipped in here, but we'll go ahead and do it. Let's do this easy one first. A stem and leaf. So stem and leaf does mess with some people when they do this. It is a different type of graph. It is a way to show a bunch of data real fast. So the nice thing about a stem and leaf compared to a bar graph, like if I was doing this as a bar graph, this is a bad bar graph, it would just look like this, right? So if I asked you, well, how many people got 236 or whatever, you couldn't really tell. You can't tell individual scores. So this one allows you to tell individual, what is this, dollar spent at the amusement park. This one allows you to see the individual numbers on here. It still has that bar graph shape to it, right? This is kind of symmetric. It still has that bar graph shape to it, but you can actually look and see these specific numbers. Here's the hard part about the stem and leaf is you've got to identify like what the key is to be able to write these numbers out. So what they did here was they put the hundreds and tens digit on the left side and then they put it on the right side. So if I were to start writing these out, it would be 219, 220, 224, 227, 228. Okay, y'all see how this works right here? So this would be 231, 231, 231, 232, 233. So you do 233, 234. So that tells you 237, 239, 241, 246, 249. Okay, so those are the numbers. It's a quick way to write big numbers or small numbers like this. So sometimes it's a 10, sometimes it's 100, sometimes it's a ones, sometimes it's a decimal. So you always go back to the left-hand column and say, okay, 231, 231, 232, 233. That's the numbers there. All right. What was the least amount spent overall? So that would be my smallest number. If you want to write them all out, you can. That would be 219. You don't have to because we can just also look right here and say 219 is my least. What was the least amount spent in the 230s? So I go to the 230s, and the smallest one right there would be 231. And how many amounts fell in the 240s? So 1, 2, 3. Or you can look right here. So it would be 3 different numbers. So that is 241, 246, and 249. Does everybody kind of see that? Most of the time, it just takes a second of explaining that for y'all to see how that works, but it is a little tricky when you first see it. I just want to generate another one. We don't have to really do this one. That's kind of the same. So like this one's talking about fuel efficiency. So miles per gallon is 13 miles per gallon, 15 miles per gallon, then 24, 24, 25, 26, 27, 27, 27, 28. So it'd be each of those. I don't know if they really do decimals ever on this one. But definitely look at that key to help you. 2/0 means 20. All right, couple more and then we're done. There is one constructing one in this topic. Sometimes Alex arranges these. Oh, this is like this. Okay. This isn't really a constructing one. This is called a two-way table, a two-way frequency table. Again, it's very popular to use in real life because it shows you a lot of data. So it says 11 women and 10 men choose comedy. So if I pick the drop-down button, I can arrange this any ways. I could do the comedy and the action as the columns, or I could do them as the rows. It'll let me do it either way. So let's do comedy and action, women and men. Okay, so you could flip-flop those and do the genres and then the male and female on the other side. Okay, so 11 women and 10 men chose comedy. So 11 women, 10 men. And then 13 women and 15 men chose action. All right, so this is saying, like, now we can look at this, like, from now on, you're just going to be given a chart like this, and you got to read it. We do this a lot in probability, but you got to identify, okay, 11 women like comedy, 15 men like action. So this is just building it, and then we will spend a lot of time, like I said, in the probability world of going over those and reading those. I think I want to... Oh, look, I could have just done these problems right here. That's fine. I already did it. I'd rather do. I wanted to see one thing real quick. If they gave you a hard one. Nope, I don't think they switch it up on you. Okay. All right. Save the last two topics, the hard topics, for the end. Oh, wait, we didn't do this pictograph one. Is it even on here anymore, or did I delete that? Because that one's super easy. Did not say, we're not going to the hard topics yet. Got to do this one, then we'll go to the hard topics. A pictograph, again, people like to use this kind of thing because it is pretty or whatever. But pay attention to the key. Each person right here equals 50 students. So how many students are at Lakeside Middle? So Lakeside Middle is this one. So you would do what? 2 times 50. So there's 100 students. So pay attention to that key down there at the bottom. And then how many more students are at Woodbridge than Jefferson? So Woodbridge versus Jefferson. So for Woodbridge, it is 1, 2, 3, 4, 5, 6. 6 times 50 is 300. For Jefferson, it is 5 times 50, which is 250. So my answer is 300 minus 250 equals 50 more students. Okay. Not super hard on that one, but do pay attention to the key because you don't want to just pick one student. Each of those little people right there count for 50 students. Now let's go to the hard ones. Which one do I want to do first? Not that one. All right, so I told you that we scroll through things fast. So I probably 0 chance of y'all seeing it if I do it like that. I don't think I have to write too much on this one though. I'll just take a screenshot at the end. News organization, sports, whatever. Like, I mean, everything in social media is to catch your attention, right? They build the algorithms, all those different things just to catch your attention and hold it. So, like, people will do things with graphs to catch your attention and hold it. So if I look at these graphs right here, before I even get started, can anybody tell me what could be misleading about, I'll tell you it's the one on the left. What could be misleading about the one on the left? What did you say?
It looks more dramatic.
It looks more dramatic. They made it look more dramatic to scare you. Like that's basically what they did this for. This is what people do all the time. Like every single one of these answers is going to be the answer I give you in just a second, because this is the easiest way to like dramatize whatever information that they're looking at. Why does it look more dramatic? Any guesses?
It's not starting from zero.
Because the y-axis, that's why I said that at the very beginning to see if you remember, the y-axis is way zoomed in here, right? It's starting at like 108 actually. So if I zoom this graph in from like 108 to 120, it looks like it's increasing a huge amount, where in actuality it's only increasing by about 10. It is increasing, so the graph on the right is the accurate way to do it. You start at 0, you can still tell the graph is increasing, but it doesn't look like it's increasing so much that like we're not going to have any air to breathe in like 2 seconds because it's that much, right? So there's an increase, but it's not like a, I don't know, they're dramatizing it way more than they should by increasing like that, okay? All right. Now, I mean, there are upsides to this, but with computers, we can zoom in and zoom out real easy. So like the graph, like I said, graph A is the incorrect one because they zoomed it in and the y-axis does not start at 0, okay? I clicked the answer there. But there are some benefits to having the zoomed in one like this, like our question on A. It says, give a rough estimate of the change in carbon dioxide emissions from 17 to 24. So I already said from about 17 to 24, 17 is at about 110, 24 is at about 120. So I suppose I will screenshot this one real quick. So like you do not have to do math. You can just kind of take a guess and it's about right. But if 2017 is about 110 and 2024 is about 120, 120 minus 110, the change is 10 divided by, you divide it by the original amount. That's about 10%, right? 10 out of 100 is about 10%. So 10 out of 110 is just less than 10%. So it is increasing by about 10%. This is, so like that is helpful. Like the data is easier to see in the graph A, but like when you're just displaying it for people to see, like the increase, you need to do the second graph. Let's save that real quick. All right, on to the next questions. Well, B is kind of like the same thing there, so I already found B. Approximate to the nearest whole number, 10. We just did that, right? 110 minus 120 is 10. So I already did that part. I will say be careful when you're on this question A. Like just don't go from the first to the last. Sometimes it will do the highest to the lowest, which isn't always the first to the last, okay? Here's the easiest way to get part C. All right, so first of all, we determined that graph A is the wrong one because the thing is off. The y-axis is off, right? So that's the first thing I want to identify is which one of these says that graph A could mislead. And where you find that on these problems is kind of right here on the last sentence. Okay, graph A could mislead a person. Graph A could mislead. Graph B could mislead. Graph B could mislead. Okay, so like right there off the bat, I know that it's not this one and it's not this one because graph A is wrong. Now you got a 50-50 chance of getting it right. So identify that first and then go read it. And this one says in graph A, the baseline is at 108 instead of 100. That's a key point right there. So that is going to be my answer. The wrong part of B is graph A, the points are same relative. And graph B, the differences between. So this one says graph B, the differences. I'm going to change my highlight color here. Graph B, the differences between are exaggerated. Graph B, differences exaggerated. No, that's not accurate, okay? It's not graph B that's exaggerated, it's graph A that's exaggerated. So that is the easy way to do those. Look at that last sentence and see which one's misleading and then go from there. And then the last one is very, very similar to that. It's going to be the same idea. Kind of. We or people in marketing get fancy and they try to use these different graphs and show these different things like this, these pictures, but you got to be careful because we live in an instant society where we want things fast and we get things fast. If I look at the paint easel, okay, look at the graph first, I guess. How much bigger is 2019 than 2024? If I'm looking at the graph, it's about double, right? I'd say I could probably fit two of these, right? Like that'd be about two of those, right? Okay, but if I go do the same thing with this, how many of these, let's just do it. How many of these could I fit inside here? I could probably fit almost 4 of them, right? So this one right here, it looks 2 times as big, whereas this one over here, it looks 4 times as big, okay? So by using a little picture, you do need to make sure they're like still accurate in there. And this is what a ton of people do is they'll shrink that one way down and there may only be a difference of, 10 or whatever, but it looks like it's a difference of 1,000,000. So a rough estimate of the change in numbers in the division between the 2 years. I would say they used half instead of double, right? So if that's 2 times, you would say this is half as big as 2019, whereas this one looks about 1/4 as big as 2019, okay? You can also look at the numbers. The numbers, we have the visitors right here, right? So if I go from 988 to 496, that's about half. Okay. So you can also look at the numbers to get that. Approximate the number of differences for the two. Oh, I just did that. I keep skipping ahead on this. 988 minus 496. What is my number? Mine. 988 minus 496. Is it exactly half? No, 492. Okay, one thing to note here. That is 492 in hundreds of visitors. Okay, so that's the answer. Pay attention to your units. I'm trying to think if this one messes with you, and I may have to generate a new ones. But like if this said, if you're talking about like a house and house sales, like instead of writing 300,000, they might just write 300. But then you might have to type 300,000 in for your answer. So pay attention to your unit on this one, because I feel like it does do that. And then the last one right here, or part C, very similar to what we were just doing a minute ago. It's not the y-axis, but graph B. So first of all, that's the thing to look for. Graph B could mislead a person. Graph B could mislead a person. Graph A can mislead a person. Graph A can, nope, it's not graph A. So it's not these two. Now I got a 50-50 chance of getting it right just by reading the first 4 words. And then the other keyword here is the italicized one. Graph B can mislead a person into thinking the decrease in the number of visitors is smaller than or is larger than. We do not, nope, it's actually thinking the decrease is big. Like the decrease is 1/4 as big. So that is what you're looking for on that one. All right, give me 1 second to generate this problem again to make sure if it changes that unit. Oh, it did it on that one. Did we read that problem wrong? I just noticed that. Oh, it says, yeah, so this is what I was talking about. It says approximate the difference in numbers in the visitors for the past 2 years. So we got 492. but it says blank 100 visitors. So the answer to this one is just 5. Because it says 100 visitors, right? As in 500 visitors. Okay, I knew it did that a little bit on these. So make sure you're paying attention to that. Like, I do not write 492. I do not write 500. I write 5 because it's already in hundreds of visitors. So it's trying to make sure you understand what unit you're looking at when you do these graphs as well. Does that make sense? So pay attention to that.